I'll leave with an understanding of some of the patterns that exist for avoiding latency in multi-region distributed consistent systems. We're going to start by talking about the CAP theorem and why consistency and low latency are sometimes at odds when your nodes are far apart. We're then going to talk about the architecture of CockroachDB Serverless so that I can provide background on the actual optimizations that we're discussing. And then sort of the meat of it will then be solving this problem where starting up a server in a multi-region deployment was taking 10 seconds when we needed it to take a fraction of a second. So I'm sure most of you have probably heard of the CAP theorem already. It's been with us for a while, and it's pretty popular on the blogs. It comes to us from Eric Brewer in 2002, and it states that a system can have these three properties. It can be consistent, which means that if you have multiple mutations, if you try to read from the system, you see whatever the most recent mutation was. It can be available, which means that nodes always respond with a useful response. And it can be partition tolerant, which means that if there is a network partition that cuts off the nodes, it doesn't violate either the consistent or the available property that the system has. Now, the common interpretation of this is that you can't avoid partitions. So your choices are you choose a CP, consistent partition tolerant system, or an available partition tolerant system.
Set.
Now, one of the dangers when you use a mathematical theorem to try to guide your system design is that the words in the theorem don't really match the words that are used in everyday engineering. And so like availability is a big one here where in the CAP theorem, it only cares about availability in the context of partitions, but real-world systems tend not to actually fail because of networking. And this is actually a point made by Eric Brewer, who was the progenitor of the CAP theorem in the context of Spanner. And I think part of why this is true is that the CAP theory's definitions of partitions tend not to actually apply to client-server applications. When you have a partition in the database, when one region is partitioned from the others, it's still available from the perspective of the client if the client is trying to communicate with the system from the internet. It's pretty common that the client gets partitioned from the internet, but unless the client is actually part of your storage system, it doesn't really matter if you have an available partition-tolerant database. The system is still down for the client. But there is an element of truth to this trade-off, and I think it comes down to communication. So if we have two nodes, A and B, that are separated by 100 milliseconds of latency between them, and we set a variable on B, we set it on A, and then we try to read it on B, there's no way around this sort of 100 millisecond tax that it takes the value to get from A to B. And I think if you look at this, there's kind of like two instincts you can have as an engineer. Instinct number one is like, well, the latency is not worth the consistency. I'll figure it out. And then the opposite is like, I'm not going to give up consistency. How do I avoid this latency? And so I think that's the revised CAP theorem, which is that it partitions engineers into two categories. You're crotchety if you prioritize consistency, and you're apathetic if you think all these hoops we're jumping through just aren't worth the effort. I'm a crotchety engineer, which is why we're going to be talking about avoiding latency. So a little bit about CockroachDB. CockroachDB is a SQL database. It's a distributed system, so you can deploy 3 to hundreds of nodes. It is this SQL over KV system where whenever you execute a SQL query, it's internally getting translated into a sequence of key value scans, key value puts, key value gets, which are then applied to a distributed key value store. So the SQL code ends up not being that distributed, but the key value store is where sort of the heart of the distributed system is. And serverless is an evolution of this architecture. So the motivation of serverless was to try to make it possible to have much cheaper Cockroach deployments. The smallest cluster you can normally have of Cockroach is 3 nodes of 4 vCPU, which is non-trivial if you only need like a core of CPU. And so the way that this works is it partitions the SQL and KV layer. So instead of being just a logical partition within the database, it's now a physical deployment partition. The key value layer is multi-tenant, so all of the tenants are sharing the underlying storage nodes, which is nice because that's where a lot of the sort of heavy lifting and durability requirements are. But they get their own SQL layer. And internally, this key value store, it looks monolithic from the perspective of the SQL clients, but it's partitioned into ranges, where each range has a sort of contiguous prefix of keys. Typically, there are more nodes than each range has replicas, so not every node is going to have every piece of data, and so you sometimes have to go to a different node to find the data you're looking for. Each of these ranges is a replicated state machine. I think this is basically the way all consistent systems are built, where you have a log that you distribute via something like Raft or Paxos, and then you send most of your operations to the leader. I think that this is a common pattern because it sort of mimics the way just logs work in a normal database, where you write something to the log and then you can acknowledge it to the user. So any patterns that exist around lock tables and normal database engineering, you can kind of drop right in. One thing that is important when it comes to latency and the performance of the system is the size of the quorum you choose. So if you have 3 nodes, you need 2 nodes in order to acknowledge your request. And if you have 5 nodes, you need 3 nodes to acknowledge your request. And so counterintuitively, often when you add nodes to a replication group, your latency actually gets better because the number of nodes you don't have to wait for increases. And so if there's variability in latency, or you have nodes that are farther away, that can sometimes help.
Right.
But the actual latency of an operation depends on, because we're trying to execute these key value operations, the latency in your system depends on how far your reader or your writer is from the leader. So if it's a read, it's just a simple round trip between the reader and the leader. But if it's a write, it's a round trip between the writer and the leader and its quorum. And so where you place the quorum is important for write latency, but not so much for read latency. Where you place the leader is important for read latency. So that's enough background into how Cockroach works, and we can get to the actual heart, which is what do we do? Why does cold starts have higher latency in multi-region environments, and how can we avoid it? So internally, this is what the architecture of CockroachDB Serverless looks like from a deployment standpoint. Every region that you can create a serverless cluster in has a Kubernetes clusters backing it. That cluster has a SQL proxy, which is responsible for routing incoming connections to the appropriate SQL servers. If there is no running SQL server for a tenant, the proxy will initiate a cold start. And what that means is it basically takes a pod, sets it up for the tenant, and then forwards the connection onto the newly started pod. So from the perspective of the client, a cold start is just a slightly slower SQL connection. And this is part of why driving down the latency is so important, because if you make them wait 10 seconds, they complain to you, I know from experience, but if you get it done in half a second, they tend not even to notice because their app has to warm caches and things like that anyway. Internally, this is what a normal cold start looks like. So a lot of work had already been done to optimize latency in single region deployments. There's a warm pool of processes that already have a TCP listener started. So the only thing we actually need to do to bind a pod to a tenant is to give it the right MTLS certificates so that it can authorize with a KV layer, because the KV layer does provide authorization so that tenants can only read their own data. And then so most of the actual, getting this TLS cert to the client, it only takes a couple milliseconds. So most of the time ends up being spent just reading tenant-specific metadata out of the KV layer, and that's the process that we need to optimize. And as an aside, so this process, it already has an open TCP listener. This isn't really related to multi-region or stuff, but that was probably one of the biggest optimizations we made, just because if you try to connect to the server before it's finished started, the connection queues in the kernel wait queue, versus we opened it, if you open it once the server's ready, you get a bunch of resets and you have to retry. And so that by itself honestly shaved 200 milliseconds off. Now, something that Cockroach does that's very normal is it stores the data about the database in SQL tables, which makes for some interesting bootstrapping problems. When the server starts up, it has to, there's some Go code written for tables that are in the critical path of the SQL layer that just pretend that they are SQL and operate it with the SQL layer in a forward and backwards compatible way. But having it all accessible to SQL is really nice from a introspection and from a debuggability standpoint. And also in tests, you can write to it, but please don't do that to your production cluster. So an example here is we have the user. So we create a user with a SQL statement. This is Postgres syntax because Cockroach speaks the Postgres dialect. And when we create the user, we end up with a row in the system users table. This row is getting translated into a key value. So the key contains the tenant's prefix prefix for the table and then the primary key. And then the value is just all of the columns that are not part of the primary key. Now in reality, this key and value are encoded in a binary format that would be hard to read, but this is the gist of the idea. And so it's like all of these reads to these SQL tables that take time. And this is kind of the before and after for what we're going to be discussing. So if the server is co-located with the leaseholders for all this metadata, we get this like half-second startup that we're targeting. But if the server is not co-located with the leaseholders, then we get 10 plus seconds, which is just unacceptable for us. So the first problem to solve here is actually how do we find the range that a key belongs in? Because the user we're looking at something like table 4, which we know is a system table, so we can just, it's baked into the binary. But we have more nodes than we have ranges, so we have to find the range somehow. And we have this layer of meta tables for that, where meta 2 has an entry for every single range, which is the first key in the range, which you can perform a scan on to find the range that you're looking for, and it'll direct you to the nodes. So in this case, table 4 Jeff, that's going to be in the range containing table 4 on nodes 4, 2, 3. On large clusters, meta 2 might itself take multiple ranges, and so there's another level of indexing called meta 1, and you do this 2-level traversal. This is all cacheable because if you talk to the wrong node, it knows which ranges it has, and it'll tell you to go away, and you can do a refresh. So, but we have to get rid of this latency because a server ends up doing dozens of meta range lookups on startup. And I think whenever you're trying to solve a problem like this, it helps to look at what the specific requirements are. So in this case, we need fast local reads in every region. We don't really care about write latency. We only write to this table when we are splitting replicas or moving ranges around, and that's not in the critical path. And we also don't need reads to be consistent. So you can sometimes give up consistency and things are fine. And that's what we do here. We execute follower reads. So when you have a raft log, you traditionally read from whoever the leader is because they have the most up-to-date data. If you don't care about having the most up-to-date data, you can read from a follower. This will be stale because they don't have whatever has been written, but you can get a quick read. And if you can tolerate staleness, this works. This is at least guaranteed to have been committed at some point, so it's like not fully eventually consistent. It's more something like read committed. But when you start reading from followers, it is sometimes helpful to have extra replicas that don't participate in the quorum. These are called non-voting replicas, and that's what we do for the system layer, or for the meta layer. We ensure that every region has either a voting replica we can read from or a non-voting replica. And this allows us to do that 2-level traversal without ever needing to leave the region. So that lets us actually find a key and read it in the database. But there's still a problem, which is that users don't actually want keys. They talk in terms of tables, in terms of columns, and there's like these 2 questions we have to be able to answer. How do we find this numeric ID that we're sticking in this table key? And then how do we get the schema that we use to decode the binary key and value? And the answer to this is just more system tables, which is the solution to most of our engineering problems. We have a system namespace, which is used to do this name traversal. So if we were to look at the underlying key here, the name is part of the primary key, so the query can just construct the key. And then we have this descriptors table, which the primary key is this numeric ID for the table, and then the value of this is a protobuf that encodes the columns, the indexes, and everything else we need in the SQL layer to interact with the table. But this information is actually still not enough to read or write from the table, because it's possible someone's going to change that descriptor out from under us. And so there's another system called leases, where we have this table, system lease, and when in the transaction that we read the descriptor, we write out a lease. And what this lease says is the schema change system is not allowed to make any changes to the descriptor that would break backwards compatibility with version 2 of the schema. So this lets us cache the descriptor in memory without needing to worry about someone changing it out from under us. There is like a protocol for getting people to give up their leases and move to new versions of the schema. But this way, again, we only read the descriptor once. This session ID is what is owning the lease. When the server first starts up, it creates a row in system SQL liveness. It's basically a random number, and a time that the session expires. And so it initially sets it to be 25 seconds in the future, and the system periodically heartbeats it so that nothing tries to steal its leases or other records it owns while it's executing. Okay, so we have reads in the critical path for schema, and we have writes in the critical path for schema. And we have to figure out, how do we get rid of the latency for these? So let's start with the writes. We can't do follower reads because we're writing. We have this requirement for fast writes on startup. And we need fast writes in every region because every region is going to have servers starting in it. We don't really care about read latency. The only things that ever need to read leases or like check whether a SQL liveness session actually exists are in non-critical cases of like recovering a schema change or starting a schema change or like recovering some internal jobs that are not user-facing. So we don't care about how long it takes to read these things, but we do need serializable reads of the lease table because the schema changer has to be able to check to ensure that there are no reads or no leases out existing that would block the schema change. And the solution to this is just to have a bunch of tables. So you can partition a table so that each region has its own copy of the data with its own leaseholders. This way, when a server starts up in region C, it just writes the row to the range in region C. If the server starts up in region A, it writes it likewise to region A. Now, you can do this where you can survive zone failures by putting a region, like a replica in each zone in the region. But you do lose region survivability. So if the entire region gets cuts out, you can't access that data. So there's an alternative strategy that is much the same, where you still partition the leaseholders. This helps quite a bit because you get fast reads in every region. And when you're writing, you only need to talk to the quorum. So you now only have to talk to whatever the closest region is before you can acknowledge the write. So there's a trade-off here. You can kind of pick, do you want to survive region failure or not? And that dictates the latency you can expect when you're partitioning data this way. And then the way that this actually ends up looking inside the schema system is the region gets added as a prefix to the primary key, which ends up encoded in the actual key that we use to store in the database. This lets us create splits in the ranges that we can then place in different locations. We do encode the region in the actual session ID. We do this so that if you see a session ID somewhere in the system, you immediately know which region the server is running in, so you don't have to like check every region to verify that it's alive or dead. But we still need to solve descriptors. So what are our requirements for descriptors? We need fast local reads in every region. We don't care about write latency again because these things are mutated during schema changes. It's not really that important to save 100 milliseconds on a schema write when you're going to go write a terabyte of data. Like it's just the wrong optimization. But we actually do need this to be consistent. We need everyone who reads from these to see the same data because they're interoperating on the underlying schema together. And we also need this to be used as part of multi-table serializable transactions. And because if we were designing this from scratch, maybe we could have gotten away with some eventual consistent protocol. But everything was already assuming that these late operations aren't latency sensitive because the stuff's cached. And it would have just been very difficult to try to go through and come up with bespoke protocols for everything. So what we ended up doing is using a feature of CockroachDB called global tables. And these are kind of the most magic thing that I'll be discussing today. And I'm going to butcher the description. There's a blog post on them. I recommend you read them if you're interested. The basic idea behind a global table is when you write to the raft log, the record doesn't have to be visible immediately. You can write the record with a time at which it becomes visible. And if you pick a time that is far enough in the future that you can get it replicated to all of your followers before that time passes, then your followers don't have to ever wait on reads. There's some nuance to getting this right in terms of number of trips between the leaseholder and the follower, but this is the general idea. So in this case, we have the log on all the different nodes. We have committed record 2, but record 2 is not actually visible until time 20. And so at wall time 10, every node replies with record 1. Now this might, on the surface, feel a little bit like just follower reads. But the difference here is that the leader and all of the followers agree on which value they're going to serve. This does come at a cost, though, which is that in order to provide consistent writes, the writer needs to wait for this record that they wrote to be visible to everyone. So they have to wait until, in this case, if the writer for record 4 would have to wait until time 30 before their commit is acknowledged. But it is still technically linearizable. So the advantage of this is we've taken basically the latency from the read path and we've shoved it all into the write path. And this is kind of our then menu of strategies that we have. So we can partition things by region so that each region gets its own copy. That gives us fast writes in that region, gives us fast reads in that region, but reads from other regions are going to be slow. We can get follower reads. This gives us fast reads in all regions, and wherever that leaseholder is, we'll have performant writes, but we give up some amount of consistency. And then we have global tables, which have this commit in the future property. And this gives us fast, consistent reads in every region, and it comes, though, at a cost of write latency. Like in practice, what this actually ends up being is we're going to have to wait for 2 times our round trip time between the quorum or round trip time to the farthest region, whichever is slower. But, so I mentioned earlier that we had this choice between region survival or zone survival. And initially what we did for all these regional by row tables is we configured them as survive zone if the customer had all of their data configured as survive zone. And we would configure them as survive region failure if they had any of their data configured as survive region failure. Now, this meant that like if a customer cared, like customers that don't care about surviving regions, they got fast cold starts. But any customers that did care saw their cold starts slow down by a second or 2, which we didn't think was desirable. So we have a subsystem called region liveness, which is another system table. This is how we solve all of our problems. We have 2 values in this table. We have the region and the time that that region is unavailable. And when we want to fence out a region, we write a record into this table that is sometime in the future, usually 30 seconds. It's important that the time we pick here is greater than the time that we pick for SQL liveness records, because when we create SQL liveness records, we read from the region liveness table to see has anyone tried to fence out our region. And if they have, we clear out the region liveness bit saying that we'll be dead at a certain time, but if not, we have to adhere to it. Doing this with clocks would be very fraught, but because we're like hooking into the MVCC transactions, we're actually like using the read on the global table to serialize that this protocol is correct. So once this time pass unavailable at, the rest of the cluster can behave as if that region is dead, which generally means that it can like move on with schema changes that have been blocked on leases. So a summary of the different strategies that we've applied. For looking up ranges, we just use follower reads because it was already trivial to invalidate their caches. For anything we need to write to, we used regional by row, and we have that configured as survive zone because we have a way of fencing out regions that we believe have died. There is one other table that I didn't talk about that's regional by row. This was like the most effort-wise in order to implement, which is why we only used it for the cases where we absolutely had to. We have 13 total tables that are configured as for global reads. Anything that was read latency sensitive, we just turned into a global table, and our problem basically went away. And then there are a bunch of tables that we did nothing, because sometimes if the latency doesn't matter, just leave it in whatever the default configuration is, and it's fine. And then just to sort of reiterate, we got the behavior we wanted. So we went and we looked at every cross-region operation, and we took it out of the startup path. So now it doesn't really matter which region a serverless server is starting. The latency is all the same as the single region case. There is a paper that we wrote that goes into detail of like how CockroachDB Serverless is built. And yeah, this is like kind of a small snippet from that paper. Questions?
When you switch to doing something like follower reads or any of these optimizations, that is like changes that you have to make in Cockroach code itself, right? This is not just configuration.
The global tables was mostly just literally alter table statements with some complexity from doing it inside the database. The regional by row tables, we did need to go make code changes to tolerate and insert things in the correct regions. Also, many of these tables are in the schema bootstrap process. So yeah, we can't just use the SQL primitives. We had to write Go code that pretends to be the SQL primitives. So yeah, it wasn't drop-in.
So does this like this was for the serverless product.
Yes.
But these are code changes that were needed. So does this impact the non-serverless product or how people are deploying this elsewhere, or?
It's kind of opt-in. So you actually, if you went into a production multi-region Cockroach cluster, you could alter your system database to turn it into multi-region, and it would configure it in the same way that we do in serverless clusters. And then at that time, you would get like the fast lease acquisition. So far, we haven't actually turned it on by default outside of serverless because they don't start up their servers nearly as often, and all this stuff is cached. So it just hasn't been a priority to finish some of the minor issues that exist when you're the one operating the system. You don't have to like fix every problem. Whereas like if we wanted to encourage everyone to do it, there are some things like removing regions from this is right now kind of tricky, which is fine for us, but customers might not like.
So the global tables, they make it so that you can send a request to any follower and it'll be consistent across leader and all followers, right?
Correct.
So you're optimizing for that request latency. But doesn't that mean that your like write to visible request latency increases because you're effectively pushing the writes out into the future in a
Yes.
heuristic fashion?
So
Under what circumstances is that like valuable behavior? Because you hand waved a little bit here of like, yeah, right here, it'll be great. But like, why do I want that versus?
I think that, so the question is, why are global tables useful if you do pay the latency on the write? Like the latency has to be paid somewhere. I think the answer is most applications tend to be chatty in the read path and not chatty in the write path. And so if you have something that is frequently read and infrequently written, the making reads fast is just more important. You read it more often. If you care about the write latency, though, global tables are a pessimization. Like, they're not a silver bullet. And I think that is why like eventual consistency is often an appealing choice, is you get fast read latency and fast write latency, and there's not really a way to get that in multi-region without trade-offs. And global tables are just one way to make that trade-off.
Can you, as Cockroach, opt into consistency for your global tables? Can you say, like, I will take whatever the latest is or the current consistent is?
Can you do a follower read on a global table? Probably. I don't know if people, so like, probably not actually, because it would be an uncommitted read from the perspective of the transaction at that time. Yeah. I think if that was the behavior you want, you would use a normal table with follower reads, where in that case you see whatever the most recent write is. And your commit will commit the moment it's replicated durably to a quorum, and then it's visible from the followers when it's replicated to the follower.
That.
I don't think I understood it correctly, but it kind of seems like your control plane is also indistinguishable from application data in some ways, where like it's all just a bunch of tables. Then say, if that is like understanding is correct, does that ever cause issues with recovery and like pathological cases of like the state of the system?
Does it ever cause problems with the state of the system?
Recovery specifically.
So we do have a control plane which lives outside the database, which we use for doing things like scheduling nodes and creating clusters. The control plane that is inside the database of like all these system tables is managed inside the tenant's key space, so each tenant gets their own copy of it. And this is done this way because that's how it worked for CockroachDB Dedicated, which is how it works for things like Postgres. It does cause problems with recovery. Like if you want to restore from a backup, the process for that is you create another cluster and you restore into the new cluster instead of like trying to fix the cluster that's down. Now, all of these are Raft replicated, so you tend not to just lose system tables. You have to lose multiple nodes in your cluster and their disks in order to be in the situation where you have to repair. That said, there are tools for like recovering the state where you try to rebuild quorum out of just whatever you have, and they often work. But those tools can't use the SQL layer. They have to be written at the layer that the storage engine understands, and they're usually acting just more on like, because like each node has its own LSM, which I didn't talk about here, but like things that work in the sort of disaster recovery case of you're not doing a backup, they have to operate directly on the LSMs.
Hi.
A question in the back?
Yeah, the global
like the global tables, where you put out a future time, but it's active. You know, what sort of like, some sort of assumptions made on the active state of clocks?
It's a good question. Cockroach, when it deploys, has a configuration for how accurate it assumes clocks are. And it validates this with the node. So if it ever like observes nodes have more clock skew than is configured, nodes will fatal. So like it's not like spend or true time where we're trying to really nail it. It's more like the clocks have to be within 100 milliseconds of each other. And if they're not, the nodes will abort. So there is some time constraints. This is needed for global tables. It's actually also just needed for leader reads because normally you don't know if you've lost quorum in your raft group. And so they're like, each leader has a lease on their log for an amount of time. And so, yeah, the system already has these time constraints.
Are you doing your own like redundant network password calling? Then how do you do that?
How do we get clocks within 100 milliseconds of accuracy?
Or it's like, how do you know which clock is wrong in a cluster?
The basic way that it works is if a node sees a time that it doesn't think is possible, like it's outside of its skew, it just ignores that RPC, like it returns an error. And then if a node finds itself disagrees with enough of the nodes around it, it just restarts itself. And so it's not foolproof. It's like there's not really a way to be foolproof with time unless, I mean, I think it's just like, there's no theoretical way to prove that you're doing this all correctly. It's just like a lot of engineering that works the vast majority of the time. Okay, thank you.